In this video, we solve problem 9.7.024 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the nth Maclaurin polynomial for this function. N is equal to 4. And notice we have a rational function. Now, when I see that, the first thing I think of is not from the Taylor-Maclaurin series sections, but I think of this geometric series. Remember, when we learned about geometric series, we said that if we have a sum that starts at n equals 0 and goes to infinity, and the nth term has this form, it's a constant times a constant raised to the nth power, that will converge to the first term, which, if this is written in this form, is a over 1 minus the common ratio. That's the number that we multiply by to get from term to term in our geometric series. This will equal this as long as the absolute value of that number we're multiplying by, called the common ratio, is less than 1. So as long as this holds, we're guaranteed that this equals this. Now, back when we first learned about geometric series, these were numbers. Now we're saying, well, what if they're functions of x? Well, the same thing holds. This could be a function of x over 1 minus a function of x. As long as this function of x has an absolute value that's less than 1, it will converge to this series. So when I see this, I see something that looks a lot like that. It doesn't look exactly like that yet, but if I look at the 2x over the x plus 1, it kind of has that form. If I look at the negative 4 over the x plus 1, it kind of has that form. So what I recommend we do is we write this as a sum of two expressions that look like that, and then find the geometric series for each part, this part, and then just expand them and keep all the terms that go up to the x to the 4th term. Now, if you're saying to yourself, why is that a Maclaurin series or a Taylor series rather than just a power series? What's the difference? Remember, all Taylor and Maclaurin series are power series, but not all power series are Taylor and Maclaurin series. So if we have something that looks like this and we can come up with a power series representation for it using this, well, if a function has a power series, it converges to a power series, it turns out that that power series is the Taylor series or the Maclaurin series in this case if it's centered at 0. So don't let this bother you. Power series are just a special case, or Taylor series and Maclaurin series are just a special case of power series, and Taylor and Maclaurin polynomials are just partial sums of Taylor and Maclaurin series. So let's make this look like this. Well, I need to have a 1 minus r in the denominator. So I'll put the 1 first. I want my r to be a function of x potentially, my a to be a function of x. So think of that as r of x and a of x. That's not multiplication, that's function notation like f of x. And I want this to be a minus r. So x plus 1 is the same as 1 plus x, but I don't want to add x, I'd like to subtract something. So rather than adding x, we'll subtract a negative x, because subtracting a negative is the same as adding. Now this has the form a over 1 minus r. And since it has that form a over 1 minus r, I can write it as a series that looks like this. So that's the sum as n goes from 0 to infinity of a times r to the n. A is 2x. R is negative x. So we can have a 2x here, and then I've got a negative 1 times x raised to the n, so that nth power can apply to both factors separately. It's negative 1 to the n times x to the n. And if you want, you can simplify. Got a 2 times a negative 1 to the n. X to the first times x to the n is x to the n plus 1. Okay, so that's for the first part, first series. The second one is similar. Make that a positive, and then we'll put a negative 4 here. I want this to look like a over 1 minus r, so I will have a negative 4 in the numerator over 1 minus a negative x. So matching that pattern again, this is my a, and that's my r. So this is the sum as n goes from 0 to infinity of a times r to the n. A is negative 4, r is negative x, and if you want, you can apply that nth power to the negative 1 and the x inside. It's negative 1 to the n times x to the n. Because if you have a product raised to a power, that power applies to both terms. And so f of x can be written as the sum of these as long as the absolute value of r, which in this case is the absolute value of negative x, which is the same as the absolute value of x, is less than 1. So f will converge to this sum for that interval. Remember, that's the same as saying that x is between negative 1 and 1. Okay, now at this point, we could come up with a way to add these two infinite series together, and I would do that if I was asked for the Maclaurin series for f, but we weren't asked for the Maclaurin series. We were asked for the 4th degree Maclaurin polynomial. So what I would recommend you do is just expand this until you get to an x to the 4th, and expand this until you get to an x to the 4th, and then add like terms. So we'll substitute in n equals 0. So it's going to be 2 times negative 1 to the 0, which is just 2, times x to the 0 plus 1, so that's just an x. And then substitute in n equals 1. So I'll have 2 times negative 1 to the first, which is negative 1, times x to the 2 plus, or 1 plus 1, which is 2. Then we'll substitute in n equals 2. Negative 1 squared is positive 1. Positive 1 times 2 is, of course, 2. 2 plus 1 is 3. Now when n equals 3, I hope you see the pattern. We always have a 2 here. This negative 1 to the n changes the sign. It goes from positive to negative to positive. The next one will be negative. If you want to check, plug in n equals 3. Negative 1 to the third is going to be negative. Raised to the 3 plus 1, which is 4, plus higher degree terms. And that's from the first series. Now we're going to do the same thing with the second series, and we want to go up to x to the 4th. So substitute in n equals 0, n equals 1, n equals 2, and so on. When n equals 0, we have negative 4 times negative 1 to the 0, so that's 1, times x to the 0, which is also 1. So we just get a negative 4. And then we will see what we get when n equals 1. You have negative 1, or excuse me, negative 4 times negative 1 to the first, so it's negative 4 times negative 1, which is positive 4, times x to the first. And I hope you see what happens here. We have a negative 4, and then as n changes, this negative 1 to the n flips from negative to positive to negative to positive to negative to positive. So I think the next one is going to be negative 4 times x squared. But let's check it out. When n equals 2, negative 1 squared is negative 1 to an even power, which is 1. 1 times negative 4 is negative 4. Negative 4 times x squared goes right there. And we have to go up to x to the 4th. So we're going to go to n equals 3, n equals 4. When n equals 3, we have positive 4x cubed. When n equals 4, we have a negative 4x to the 4th. The next one would be positive 4x to the 5th. But we're not so interested in that because we want the 4th degree Maclaurin polynomial. So that means we need to keep all of the terms up to the 4th power of x here. So we have a constant term of negative 4, and then 2x and 4x is 6x. Negative 2x squared minus 4x squared is negative 6x squared. This one plus this one is positive 6x cubed. This one plus this one is negative 6x to the 4th. Now, if we had chosen to rewrite this as a -4 plus a sum of two series, we could have done that. And then we could have expanded that to get this. But I think in this case, since they were only asking us for the Maclaurin polynomial rather than the Maclaurin series, it's easiest to just write these two geometric series and then add like terms up to the x to the fourth term.